Why is TCP still the top internet protocol?
TCP, it works. A lot of cases, it's good at what it does, and it solves a lot of complexity and problems for sending things across the internet.
The dominant protocol of the internet since RFC 793 in 1981. 1981. You weren't even alive, right?
No, I wasn't.
Now you're starting to get some gray hair. 1981, TCP came out. And if you look, that's what most apps use all day long to this day. So why are we still using an 80s protocol?
So there's different layers of networking protocols. So you hear IPv4 and IPv6. Those are what we call layer 3 protocols. They transfer over the network. They give you addresses between different computers on a network. And then on top of that, you have the transport protocols, layer 4 protocols, and TCP and UDP are the big examples of that, the common ones. So if you know that you want to send data from one computer to another computer over a network or over the internet, you have to know the address of it, and that's the IP layer, and then you have to transport the data, and you have some protocol that does that. And
so they talk about being a guaranteed protocol.
Right.
So it gets you, the packets you send arrive in order. It makes sure that none are missing. Yeah. What else does it give us here?
Ensuring that they arrive there. So when you're sending data across the internet, dropping packets is one concern. Packets can get lost. They get dropped out of a buffer, or something happens at the physical layer that they get lost. So it has an acknowledgement system for making sure that those packets get through, and it can resend them, retransmit them, and it makes sure that everything arrives in order. But then you also have different speeds of links when you're sending. Your internet connection does one speed, and then you have fast connections out on the internet. It's able to negotiate and detect how fast across the whole path between one computer and another can it go, and it can try and maximize that speed. It also packet sizing. Different links can have different maximum sizes that they can send. Certain cellular connections might have a smaller packet size that they can send because they have more overhead, but then out on the normal internet links they can do a slightly larger packet. It's able to detect over that whole path what size packets it can use. Fairness is another big one that makes it useful for the internet. When you have a bunch of different devices with TCP connections at the same time, they all balance out so that everything gets a fair share of the bandwidth, and you don't have one TCP connection hogging all the bandwidth from the other devices that are trying to use it, which is good for the internet. You don't want one person able to hog and monopolize all the bandwidth from a connection.
Unless it's me.
Right.
I should be allowed to hog, but the rest of you. Yeah. So it's guaranteed. What is the guarantee?
It's guaranteeing that all the data that you send from one side will arrive at the other side and be delivered in order and all get there, that you're not going to have any data that's missing or mixed up or out of order. Makes it easy.
You will get an error.
Right.
That's the guarantee. That it will either arrive and be delivered in order, or you will get an error. It's not your money back. You'll get an error. So there's no confusion. You'll never send the data, think it got through, but it turned out they didn't get it. No, it either got through or you got an error. Real trivia thing. It's not an exclusive OR. It can deliver the data and give you an error. And it's clear to see, if you really think about it, how this happens, right? You send the data to the other guy, and when he responds back, I got it, you unplug the wire just before it arrives. And, there's no way for it to know for a fact that it arrived, so you get an error, but he gets the data. It's kind of a rare scenario, but it's one of these interesting little twists. They said OR, they didn't say exclusive OR. So how does this vary from UDP?
So UDP is another popular transport protocol for sending data across the internet, but it doesn't guarantee that all that data gets through. It's more of a best effort. So you're sending these packets, and the packet may get dropped in the middle and just not show up on the other side. And that's part of UDP, that your application has to think about dealing with that there might be data missing, where TCP takes care of that and just solves that for that complexity. It takes it away. The application can just worry about, this is the data I want to send. So UDP gives you more flexibility in certain way. We can get into different situations where TCP might not perform as well, and where you might want to use UDP. But UDP, doesn't have any guarantees about the data getting through in any particular order, or that it arrives at all. It's more just a best effort of trying to send something. There's no acknowledgement that the other side got it. You'd have to implement all that stuff on top of UDP if you want to kind of emulate some of the features that TCP gives of guaranteeing the data gets through.
So one thing you mentioned, MTU, maximum transmission unit, right, and packet size, right? So bigger packets let you go more efficiently, right? You can send more data at once. And it's more efficient because there's extra packet headers at the front you have to add to each packet. So the smaller the data, the more your internet connection is headers, so less efficient. So jumbo packets, or jumbo frames, if you're talking about Ethernet, are very big packets, right? Ones that are bigger than 1,500 bytes.
Right.
You talk about why don't we just have internet connections that let us send 1 megabit frames and packets?
So I think there's a big kind of historical aspect to it, that a lot of things have been implemented with 1,500 being the limit, and you can support big frames across local networks. There's support for jumbo frames within Ethernet sending across a local network, but a lot of the internet infrastructure, I think, was designed to only support 1,500 as the limit, and I think changing a lot of that would be probably a big deal. There's also the balance between, if you have really fast links, being able to send bigger chunks can be good, but if you have slower links or unreliable links, that's bigger chunks of data that you're potentially losing at once, or if you even just lose a little piece of that, then you can lose a bigger chunk of data, a lot more that you have to resend or handle losing. So it's also a balance between...
So responsiveness, because your whole internet connection freezes up when it's sending a packet. Right now, packets are so small you never notice. But there's also the error thing. Unlike a wireless link, the bigger the packet, the higher the chance there's some interference during it. Gets too big, you get more and more likely to lose the packet, and you have to start over and send all that again. That said, I suspect that if people were starting over, 1,500 bytes wouldn't end up being the default the way it is today. I think we'd have something more.
Either something more dynamic where you can negotiate, or some larger limit, or because the maximum size of an IP packet, you can have up to 65,000 bytes. So there is support at that network layer for bigger packets.
Yeah, and of course, TCP, it's so hard to replace, right? People have tried before, and the problem is you end up needing all the routers in the middle to know about this new protocol. And TCP, it's so widely used that network cards now have big sections of TCP implemented in hardware. You're not even doing it in software. If you came up with a new protocol, you have to do it in software. So even if it was better, it would likely seem slower because you're doing it in software where TCP gets done in hardware.
Yeah, the one approach that has gained some traction is QUIC, which is basically building a TCP-like protocol on top of UDP. So it gives them some more control over how the packets are handled, but they're implementing a lot of the features of acknowledgements and congestion control and everything on top of UDP instead of just on top of bare IP packets.
And so, as some of you pointed out, UDP is not reliable. You send the message, it gets there or it doesn't. Routers in the middle are supposed to do their best to get through, and if they fail, they don't have to say anything. But when you build another protocol on top of it, like QUIC, even though UDP is not reliable, you can build in, when you get this UDP packet, send back another UDP packet saying whether or not you got it. You can build a reliable protocol on top of it. Mm-hmm. So they built this thing which is very much a competitor to TCP.
Yeah, it's being used a lot by Google in, I think the Chrome browser, when it's talking to a lot of the Google services, YouTube and other things, it's using QUIC a lot of the time.
The QUIC guys at the beginning at Google were very honest that they were trying to build a replacement for TCP that would work better for YouTube. They weren't trying to replace it everywhere on the internet for every app. They were trying to build a better protocol for YouTube. And I think they did, right? They focused in rather than try to make everyone happy. They picked one website owned by their employers and said, how do we make this better? And I think they came up with a protocol that helps a lot of people, but particularly people doing websites and stuff.
Right. And so now you have HTTP3, which is built on top of that, doing HTTP over QUIC essentially, which is over UDP. So a new version of HTTP is using that. So UDP-based protocols are getting more popular, and there are some benefits and drawbacks to both TCP and UDP.
So in Speedify 15.9, you have this PEP thing, Performance Enhancing Proxy. On older router devices running Speedify 15.9 later, there's this new feature, which I know some people are already calling our TCP Accelerator, which is also a valid name for it. But can you explain how that works?
So it's essentially intercepting the TCP connections when they come into the router. So normally Speedify has a virtual internet adapter, and when packets come through, they would go into the Speedify's virtual adapter, and Speedify handles sending them out to the server over different internet connections, and they go out to where their destination on the internet. So instead of going through this virtual adapter, Speedify's intercepting all the different TCP connections that come in and ingesting them into Speedify that way. So they terminate at the router. Speedify is then able to send, technically not using TCP, but all the data across our Speedify transport protocols to the server. And then on the server side, it makes a new TCP connection to your final destination and sends it from there. So it's breaking up the link. So, when you're going over long latencies, the longer latency, the more impact it has on TCP performance, the longer it takes for acknowledgements to get back. So that can, if you have a kind of unreliable or lossy link, the higher the latency, the more impact it can have on TCP's performance. So by breaking up into these segments, you're just having TCP going between your client device and the router. That can be a very fast link, and you're sending the data over Speedify, and then it's just between the Speedify server and the destination. It's splitting up into these different TCP segments, and so the latency of the whole path doesn't matter as much, and you're able to avoid some of the slowdown problems with TCP on more variable or higher latency links. And then it also, where we get a lot of the performance improvement, it allows us to more efficiently process large chunks of data from TCP. So when we're terminating at the router device, we're able to read in big chunks of data from these TCP connections, where normally we're limited by whatever the network limit is. We were talking about that MTU, where the network link between your router and your client device is usually a limit of how large these packets can be. We're now able to read in these larger chunks of data from the TCP connection because it can group them all together in the operating system and give us this big chunk of data.
Wi-Fi often has, 1480 byte maximum packet sizes. So even if you have an internet connection that does jumbo packets, without the PEP, we can't use it because you're coming in with these little packets, and that's all we have to send, even though the internet says, hey, I'll take a big connection, a big packet. But now with the PEP, we'll take a bunch of your little packets and put them together into one big efficient packet and send it out. So, yeah, I'm really seeing, 70% faster results.
I mean, yeah, even more than that.
You had somewhere you were getting 600%.
Right, yeah. A lot of times, if you're maxing out the CPU on this device, which isn't hard to do on these little lower-powered routers, but yeah, if you have a sufficiently fast internet connection, gigabit internet connections, we were seeing results 6 times faster through the router than we were seeing previously without the PEP when you come down to CPU-constrained performance.
So in conclusion, TCP is going to stay the king of the internet for a long time because it just does most of what you want. And, there's flexibility. People like us are showing up and doing things to accelerate it more. People who make the hardware cards are building stuff in to accelerate it. So at this point, it has so much momentum, and it's built into every router. You can't get a router that doesn't support it.
I guess the other important thing to note is that TCP has evolved over the years. There are parts of TCP that can change. Namely, a big part is what they call the congestion protocols that control the rate at which TCP is sending and how it reacts to packet loss and to different signals. So originally, it was developed back in the 80s using an original protocol that was very susceptible to loss. If you lost a packet, it would drop its speeds in half and really back off and really slow down. So any links with packet loss could really impact the performance of TCP. It could really slow down the performance. And then there have been improvements over the years, both to handle faster internet connections as well as more unreliable internet connections, improvements to these congestion protocols. You have different ones. QUIC was a big breakthrough of that. If you lost packets, it would just drop down a little bit. And then if you lost some more packets, it would drop down a little bit more. Follow this kind of QUIC curve. The same thing when it's increasing. It wouldn't do big jumps up. It would do a little jump up first and a little bit bigger jump, a little bit bigger jump to find how much available bandwidth you have. So it would converge in the right speed faster, but also not get thrown off just because there's a little bit of packet loss. And then even more recently, BBR is a big congestion protocol that's used a lot now. It's really trying to optimize your bandwidth while limiting how much buffering there is going on and how much extra latency you're adding. So it can really discover what's the maximum capacity that can put on this link.
Bufferbloat.
Right,
Bufferbloat is bad. If an internet connection can't go as fast as you want, it should tell you I can't go that fast and not just stick it in memory to send it later, because that ends out confusing everything, right? Your computer thinks it has a faster internet, so it sends even faster. But they fix a lot of this stuff in BBR and the other adjustments to protocols to deal with buffer bloat. Does Speedify still use HTTP 1.1 somewhere? Just saw a video. HTTP 1.1 must die about how vulnerable it is.
I don't believe we're using 1.1 anywhere. I mean, when you first connect, I think a lot of times it initially negotiates up to a higher version, but I don't believe we're using on our servers anywhere or any of the HTTPS protocol that we're using. I don't believe we're using 1.1.
I think UDP is not reliable. It sure isn't. So it's a new improved alternative over TCP. You know, for certain use cases, there's QUIC, but like I said, they really focused on being the best protocol in the universe for YouTube. Closer you are to YouTube, the more QUIC will seem better than TCP.
I also point out sometimes you don't need a reliable protocol. You know, certain games or other things. Sometimes you just
if you're doing a voice call, you know, it's okay. It's better to have some gaps than to have one person on the call falling further and further behind as the software tries to hide the gaps from you, right? So sometimes you don't need that. Does new tech like mmWave require better protocols in the future? So mmWave is up at like higher than 6 gigahertz, 9 gigahertz, 12 gigahertz. The interesting thing, right, it's sort of short range. It's so short range and it's so unused and there's so much bandwidth. It's kind of, 9 to 15 gigahertz that people are grabbing 500 megahertz at a time. They actually can get multi-gigabit connections. You need fancier antennas or to be really close, but that's not our problem here. So if you suddenly have a wireless link, that's 5 gigabits. I mean, the obvious thing is, I guess we're sending bigger packets. That might actually be it. This nonsense of only sending 1480 bytes over wireless links probably goes in the trash when the wireless links are that fast. You have 500 megahertz wide signals. So,
and that's where you can see some of the limits of TCP when you get to really high speeds and where they've had to make tweaks and improvements, and you start looking at 10 gigabit Ethernet and 40 gigabit Ethernet. To reach those high speeds, sometimes you need to make tweaks on what's possible, or it takes time to ramp up to those speeds, depending on your latency and everything. It can take a while for for TCP to negotiate up to the full speed of the link. So they've made different improvements to those protocols that adjust the sending speeds and all that. But there could be potentially other protocols that work better over those depending on what you're trying to accomplish.
Speaking of IPv6, it seems to be gaining momentum to replace IPv4. I am not seeing that.
We did a whole video talking about this a few weeks ago.
I am not seeing that. I am seeing negative momentum. I am seeing people giving up on IPv6 because they've realized it's never going to happen. The only new spot, the new interesting thing, right? People for years have been saying, well, the problem with IPv6 is it doesn't enable anything new. It just enables more computers. But if your computer's already on the internet with IPv4, what do you care? There is something new it enables now. Thread and Matter in a home Internet of Things. These new protocols where they're trying to give IP addresses to every light bulb, every light switch, every dishwasher, every stove, every one of the little security things on your windows for your alarm system to see whether or not the windows are open. They want to give all of those IP addresses. Only IPv6 is supported. So that whole system is IPv6 only. So we'll see. It's been muddling along. They're coming out with new versions of the standard multiple times a year as they add. They've had so many things. They add dishwashers and stove tops and hot water heaters and solar panel arrays and light switches and dimmers. It is growing and growing and growing, and more devices are showing up. That really takes off. That seems like finally a reason. You need IPv6. You can't have your shades go up and down by themselves when you enter the room. That's probably, to me, the most exciting thing about IPv6. With IoT, are we running out of IPv4 slots? Yes. And that's why, the new standards on IoT, Thread and Matter, they are IPv6. Thread is 100% IPv6. Right, it's this new wireless standard for low power. It's low speed, but it's low power. So that you can have little battery-powered IoT devices, little sensor on your door to tell whether it's open or closed, and you only have to change battery every couple of years. Those are getting IPv6 addresses. He's got this IETF has laid down the line that they're just not going to do IPv4 for that. They're not going to play around with mega nats or whatever. Those are all IPv6. So, IoT, Internet of Things, that is where we are really going to see it. Does FastTCP overwhelm downstream bandwidth if you use Bufferbloat-aware queuing mechanisms that minimize delay?
Yes and no. So one, it depends. We're talking about the different congestion control algorithms that the TCP uses. So you can get different results depending what you're using there. But traditionally, the original congestion control, they will push your connection to the point where it starts dropping packets and they slow down. So a lot of times that means you're filling up whatever queues, you're bloating the buffer, and to the point there the buffer's overflowing, you're dropping packets, and then it's slowing down. So it's basically saturating however much you can get out of your link, and it's adding more delay in there. We were talking about BBR as a congestion protocol. It tries to limit how much of that queuing it finds just the point where it's filled up, just starts to hit the buffer. You start to see a little bit of increase in latency, and then it stops there and doesn't try to overflow the buffer and tries to limit itself. So you'll see better results in that respect with BBR. But then, depending how the Bufferbloat-aware queuing is working, sometimes it can send congestion signals on packets to tell it to slow down. And so that can help it to limit and not overwhelm. TCP also tries to we were talking about fairness. If there's other TCP connections also trying to use, it's going to try and balance out fairly so that everybody gets their fair share of the bandwidth. So yes, it has the ability that it can drive a lot of extra delay in there, but it'll also back off and try and be fair about how much bandwidth it's using, and you can get different results depending on different congestion protocols.
And Thread helps Speedify. Probably the other way around. I mean, Thread shows up as this network adapter where you can do 200 kilobits per second to talk to your light switches. Speedify shouldn't try to jam data over that. That would be a mistake. I do think that probably in the near future we should do a little bit more testing with Thread devices and Speedify and see that we are helping them get to whatever they need to get to. Although most of that stuff ends out, you just want local on your LAN anyway, right? So that your Alexa can talk to your lights, so that your light switches can talk to your lights, things like that. It's mostly a local technology, but I assume clever people will come out with ways to want to do this on vast scales. Yeah, so that the new Apple Wi-Fi chips support Thread right in them. My Eero router supports Thread right in it. My Alexa support Thread right in them. I have a whole Thread network before I had the first device. So, Speedify 15.9 is out. We spent a while talking about all the new things in there. In addition to bug fixes, you can now bypass by IP, by host name, by port, so you can really customize those bypass rules. For those with router devices, there's a new performance enhancing proxy that leads to massive speed ups. It's not on by default, but if you have a router license in settings, you'll see performance enhancing proxy. Turn that on. It's speeding me up, 75%. There are, other scenarios where it speeds you up more. It really makes a huge difference. Really accelerates your TCP. So you should give that a try if you haven't already.
Yeah, and definitely let us know how it works for you. I mean, it's a new feature, and we're still making improvements to it and stuff. So if you see any issues with it, definitely let us know.
And I think that's everything. So if you haven't, you should update too. 15.9. This is a good release. All right, thank you everybody. Check out those videos on YouTube. Upgrade Speedify, and I'll see you all online. Thanks everybody.